recording going. So today, we're going to wrap up. I specifically requested to give you guys a taste of neural networks. So we're going to do a one-day introduction to what the crap that means, which is related to YouTube, I promise. It's not that I expect you to be able to program a neural network afterwards. More so, I just want to make sure I want to make sure you know that they exist, that you can make them, and actually make them pretty easily, especially in Python. And they can be used for a variety of things. There are a lot of applications in oil and natural gas. Also, a number of kind of interesting applications outside of that. It's more of a enjoy the ride kind of day because it's an interesting topic. Sound like a plan? Cool. So, YouTube. YouTube's cool, right? One, because the videos are sweet. Two, in how it figures this out. So, YouTube, in a nutshell, this is a bit you who probably know already. So you have a whole bunch of content that's made. You have these crazy huge servers that store all that content. We're talking about how additional hours of content being added every second. And then somehow from these trillions and trillions of videos, a subset is selected for you. Question is, how the crap does that subset get picked? And the answer is a neural network. And this is kind of a strange introduction, perhaps, but you'll see the connections in a minute. The idea is that all that. How do I say this? The idea is that you can have videos that contain a myriad different content, right? And that is called, and you can translate at least some of that via tags, but just seeing like tags of like I don't know, skiing isn't necessarily going to give you videos that you would like if you like skiing, because it might be like an anti-skiing video that comes up, right? There has to be something that kind of translates it for you. Another way of thinking about it is that if we look at something, we can look at a desk, say, and infer a lot of characteristics about it based on its context, right? If I see a desk per se that is long, let's call it tall, small, and has a slightly inclined top to it, I think, oh, that's something that I'd want to use if I was like speaking, right? It's like a podium. If it's a broad, flat desk, I might think, oh, it's called that has very short legs. Maybe the top's only about waist high or so, and it has his kind of a thick reinforced top. I think, oh, that's like something that I can knead bread dough on. It's at the right height for which called baking or something like that. We infer a lot based on context, not just characteristics of the object itself. So what a neural network does is that it's more complex than just an if statement. It's more complex than just saying, okay, this characteristic matches exactly what I'm looking for, therefore it must be what I'm looking for. Neural networks are more nuanced than that, because that's a question that we could ask right now in code using an if. It doesn't contain context. It's just one thing. Or even you can add a bunch of ands and have like a bunch of things. Neural networks are more nuanced. What they do is they try to imitate our way of interpreting the world by adding context clues. So see if we can characterize this more. So here we go. So yeah, let's say it like this. So if I see something, like how my eye works, I see I see something, it comes in, sparks some neurons, and eventually that like goes through a bunch of other neurons, fires some more neurons, fires a few more neurons, and eventually that manifests as some form of cognition. I'm not really entirely sure how. When we first, as a scientific community, started looking at this neural process, we said, okay, so you have some inputs, that goes through some other layer of processing, and then it produces an output somewhere. That's that, we call that processing layer is that hidden layer. It's not the input, it's not the output, it's just something in the middle that interacts. It kind of makes sense, right? What we found out is that it actually looks more like this. You have a bunch of inputs, some of them feed into other things that we thought were inputs. Some of them go to that hidden layer, and then they come back to the inputs and then go back to the hidden layers. Some of them feed off somewhere into space that we don't know where the heck they're going. Some of them don't feed anywhere that we know of. It's a jumbled mess. And to quote a Caltech neuroscience researcher, roundworm has exactly 302 neurons. We have no friggin' idea how the thing works. So in terms of like how a brain actually works, how a true organic neural network works, we have no friggin' clue. We're trying, but that idea of how there's multiple processing layers and some relationship between these different inputs, that's kind of the takeaway from this. What I thought was kind of funny was in terms of processing power. So most computers on campus are like down in the what you call gigaflop region. Most advanced computers in the world are in like the teraflop region in terms of like processes per second. And like rat brains are do more computations per second than our present supercomputers, which is absurdly awesome. So that was a little tangent there. I mean, and maybe it was a little fast, but what does this mean? Oops, there we go. So for YouTube, it works off of that idea of we have some inputs. We have your age, gender, your demographics, what language you speak, languages that you've watched, so on and so forth. All those feed in. And that's the context of the YouTube decision-making tree. It starts with that. Then it says, okay, what videos do people in your demographic also watch? It pulls all of those. And what the folks over at YouTube and Google have done is they've trained the decision-making process. They said, okay, which call thousands of people with this particular demographic like these kind of movies, we're going to feed in a whole bunch of context for those people and say these are the sorts of movies that the neural network should put out. So they train these hidden layers of neurons to kind of direct those inputs towards those kinds of outputs. So even as the content that you could pick from changes, it can still match you with things of the same characteristics. Does that make sense? Cool. If you want another way of thinking about that, you could, one example that I saw was with wind turbines. On a wind turbine, you have vibration sensors, temperature sensors, strain gauges, acoustic sensors to listen to how the structure is doing. You have all these different sensors. Question is, the challenge is that input from any one of them that says there's a problem doesn't mean that doesn't tell you how bad the problem is, or neutral, or is this something that will hold that can keep on operating for days, weeks, or hours? How fast do I have to get out there and fix this, right? Because if the turbine blade shears off, that's going to be problematic. There's a turbine that blew up literally in Scotland. I think it scattered fiberglass over like a mile radius. Not good, I might imagine. So you want to be able to at least stop the thing from running, but at the same time, you don't want to lose money. You don't want to lose money. So it behooves you to understand how bad a fault is. And any one sensor can tell you that there's something wrong, but you need the combination of them to tell you exactly what's wrong and how bad it is. This is why we love for cars those old timey mechanics, right? The ones that can just listen to what's going on and say, "Oh, your water pump system's bad." You just kind of stare at them and go, "What?" But that's why we like those people, because they can synthesize a number of different inputs at once and tell you exactly what's going on. So what the guys on this wind turbine are doing, they said, okay, well, we have all these sensors. We know that we can reproduce a fault in the lab, measure it with these sensors, and use that data to train the computer what these different faults look like when it sees all these different sensor inputs at the same time. And that's kind of the power of a neural network. You can take a whole lot of inputs and synthesize them all together to tell you something like the amount of service life remaining in your wind turbine's gearbox or blades or whatever. It's super, super cool. And you can make them as complex as you want. You can think of it as like an input layer, if you will, one set of inputs, one set of outputs, and some processing thing in the middle. And say, hey, could put a whole bunch of those together. So in theory, you can make some more complex connections. So one output gets connected to the decision from that first hidden layer, connected to a decision from that second hidden layer, and kind of nuance what the output is more. You have options in the sentence, but that's a little beyond the scope of what we're talking about. The basic idea here is that in neural network, the idea behind it is to let the computer make connections between these disparate inputs, be it either these sensors for a wind turbine, watch history, demographics, etc. for YouTube. I just looked at a bunch of papers from one Petro that were talking about characterizing porosity. He based on like 32 different well log parameters. There's just stuff on characterizing geology based on various seismic tests and so on and so forth. You can use these for anything, really. And what they excel at is essentially just being a really, how do I want to say this? Robust way of interpreting multiple inputs. It's what we kind of want to do. I mean, that's why we're here, right? That's why we're in school. We want to get background and intuition, so when we go into the field or into a full-time job, we have something to draw on. But we can also use a computer to do kind of the same thing for individual, very specific problems. So we're all on board with that. Let's play the game with an example. Here we go. All right, so here's the code. What this code is doing is I have a particular set of input data here. It's pretty simplistic. It's just it's 3 columns of zeros and ones. You can think of each column being kind of a different. Each column being a different set of inputs. It doesn't have to be zeros and ones. I just chose it. So you can say, like, I don't know, the first just rows a flow. First row is a flow meter saying if something's high or low. Second one's like a magnetic sensor, so on and so forth. Each row is a different input. What those all correspond to is this output, this Y. Okay. So all those inputs correspond to this particular output. So for a wind turbine, it'd be like, let's call it that wind turbine example. The X might be different. I'm going to say different. What is the word? Diagnostic sensors. The Y might be a measured service life, based on some tests. And I want to relate those two, because because as shown, different combinations of sensors might indicate the same problem or the same amount of service life, which makes sense. Like, there are different ways for your car to die, right? There should be different ways for anything to die. There are different combinations of problems that can result in the same thing. And we're going to ask the neural network to relate them all. So how we do that, one way of doing that, is by assigning these inputs different weights. Question is, what the heck weights do we choose? And frankly, no one knows. But that's what it's called. But that kind of starts the most important part of the process. So when we make a neural network, first thing we have to do is gather some test data. Oh, that was terrible. Which would be like all this stuff. Something that characterizes what the heck's going on. The next thing we have to do is train the model. So the model is that Y equals some matrix of coefficients times your X. So this is a coefficient matrix. This is something that relates those inputs and the desired output in some way, such that regardless of what my input is, the relationships described by my test data, rather that all these inputs cause this kind of an output, those coefficients are selected so that that's always true. So this is like the biggest problem with neural networks too, right? When I say problem, what am I kind of getting at? Like, what looks like it could go wrong in this process? If I'm trying to find some set of coefficients that relate just this data to just these outputs. What does this suggest about neural networks? What if I eventually put in an output that's outside this data, that's still in the real world, does this? Will the neural network be able to predict that? No. Why? Yeah. So if I put in another, and let's see if this is the same thing that you're saying. I think that it is. If I put in, if once I develop my neural network, once I figure out what this coefficient matrix is that relates these x values, these y values, if I get my sensor data one morning and I put it into my neural network and say, tell me if this is going to blow up today. If that combination of sensor data actually means something that actually means this, but it's outside of kind of my test data, the neural network's going to not know what the heck is going on because because the test data didn't include it. Like if I get a strain gauge, but I've tested it on temperature, vibration, acoustics, and strain, they'll say, "Oh, what you're doing? Oh, I don't know what that thing is." Or if I have a really elevated measurement that is far outside anything that I've trained my neural network on, anything I computed this coefficient matrix with, the neural network's not going to know what to do with it because it's beyond what it knows. So neural network is incredibly powerful, like coding. Like you guys have made some very flexible codes in the past few weeks. But at the same time, if we put in something that's outside of what it's trained to look for, or outside of what it's made to do, the code can't do anything, right? Like what's called something we've learned about units, right? Like units are friggin' important because the computer just sees numbers. It doesn't know that something's atmospheres, pascals, or millibars. So the neural network, by extension, is only as smart as our test data makes it. So one of the most important things for a neural network is that you get a large quantity of test data to train it on, that you compute this coefficient matrix from, and that it covers any and all measurements or any and all information that you expect to feed into it. You can kind of think of it like the first time that you saw a car, and if someone asked you what was wrong with it, you go, "Oh, I've never seen a car before," right? It's the same thing in here. The neural network is only as good as the context that you teach it on. Same way, like if we go to troubleshoot a car, our knowledge of how to do it is only as good as our knowledge of the context of the problem. Do we know how a car works? You know how an engine works? You know what's connected to it? Blah, blah, blah. So a neural network is very dependent on this, on this particular part of the process, where we stick in test data, select what that test data is, and then use that to develop relationships in the code between what inputs it could have and what outputs that has. Cool beans? Sweet. All right. So once you do that, and that's kind of the bulk of this code. The bulk of this code is just saying, okay, here's an input here. We'll feed it through two layers of a neural network, and see how close we get to what our output is. And based on how far we miss it, we'll change that code. We'll change up that coefficient matrix, and we'll do that. In this case, we do it 60,000 times, which takes like about a second or so. Let's up that a little bit, do 100,000 times just for kicks and giggles. I need to mark this against the top of the screen again so I can see the bottom. There we go. All right, and eventually it'll pop out of that, and we'll have a coefficient matrix. At that point, I'm going to stick in a thing of X. We're going to see how close we get to the actual, a matrix of X, and we'll see how close we get to the actual values. Cool beans? So wait for a little while. Okay, cool. All right. So two things. One, this figure, this shows how the output error changed during the training period. The training period being the time where it's kind of figuring out what the coefficient matrix is. The x-axis is what iteration you're on. The y-axis is your output error, or how close the result is to what it should be, based on how those coefficients changed. So after 100,000 iterations, we're getting close to we're getting close to 1,000th of the right answer, which isn't terrible, not great, but not bad in the grand scheme of things. And that only took a few seconds, right? So that's kind of cool. Did I do any interpolation in that time? No, none, zero. All I'm doing is linking this context to what the output should be, and coming up with a couple of coefficients that make the math work. That's all I'm doing. And if I look at the output should be 1001. The code says 0.998, 0.03, 0.02, 0.997. That's pretty freaking good for about 5 seconds of work and no interpolation, right? So this is a really dumb and stupid simple test, but this is kind of the premise of what a neural network could do. You take in a bunch of context, you let the computer figure out relationships between those different bits of context, those different bits of information, and what it spits out is a set of coefficients that you can just apply to whatever your inputs are, or it might just make a self-contained model, just a function that you can just plug things into, and it tells you what's going on. It's a really, really cool tool. Python has a lot of built-in libraries for it too. I'm not going to get into those too far. And I never liked teachers who introduced something that they wanted me to use on the last day of class. So cheers. All right. So that's my crash course in neural networks. Any questions? Thanks for riding the brain train, pun intended. Are there any questions on the final project? Cool. I look forward to a plethora of wonderful compressibility calculators on Wednesday. Cool. Then all I got is idea surveys are live. So grab them out, do them up, and when you're done, you're done.